distinguished colleagues and distinguished guests. It's March 5th, 2021, 2 p.m. Moscow time. We're beginning the panel session for the defense of the thesis by Valeriia Mulloiarova. A thesis is submitted for the academic degree of the candidate of sciences in chemistry. The specialization is 020004, physical chemistry. The topic of the thesis is hydrogen bond and proton transfer in self-associates and mixed complexes of phosphorus-containing acids. Under the order issued by Alexander Gnyotov, the Academic Secretary of St. Petersburg State University, as of December the 7th, 2020, number 11028/1, I, Alexey Viktorov, Doctor of Sciences in Chemistry, Professor of St. Petersburg State University Physical Chemistry Department, was appointed the chairperson of this dissertation board. The order also approved the candidacies of the members of our board. Let me introduce them. Alexander Vasilyev, Doctor of Sciences in Chemistry, Professor of the Organic Chemistry Department of St. Petersburg State University, Director of the Institute for Wood Biomass Chemical Processing and Technosphere Safety of the Kirov St. Petersburg State Forest Technical University. And the following members of the board are working remotely. Denis Markelov, Doctor of Sciences in Physics and Mathematics, Professor of the Nuclear Physics Research Methods Department of St. Petersburg State University. Do you see us and hear us, Denis? Yes? Yes, I do. It's okay, thank you. Then, Natalia Belkova, Doctor of Sciences in Chemistry, Russian Academy of Sciences Professor, Deputy Director of the Nesmiyanov Institute of Organic Element Compounds of the Russian Academy of Sciences. Natalia, do you hear us and see us well? Yes, yes, I do. Thank you. Thank you. And Martin Polisak. Professor, do you hear us?
Yes, very well.
Done.
Okay, we have simultaneous translation.
Martin Polisak, Doctor habilitated in Chemistry, Professor of the University of Lodz, Poland. Do you hear us and see us well?
Yes, I hear very well. Hello.
And we also have our candidate for the degree, Valeriia Mulloiarova. And we also have the thesis supervisor, Petr Tolstoy, candidate of Sciences in Physics and Mathematics, Professor of the Physical Chemistry Department of St. Petersburg State University. Distinguished colleagues, in order to improve the quality of our connection, kindly turn off your microphones, but don't forget to turn them on when I give you the floor. I would also like to inform you that the panel session of the dissertation board is being recorded and broadcast on the St. Petersburg State University website, and it is also interpreted from Russian into English and vice versa. Currently, we have an email address posted on the page with live broadcast of the board session, and all listeners can submit their questions to Ms. Mulloiarova online. The questions regarding the thesis or scientific discussion. These questions will be forwarded to me by our technical service, and I'll read them out during the discussion. The questions must be related to the presentation and the content of the thesis, and don't forget to give your name and position if you submit a question. The questions that have nothing to do with the scientific discussion or dissertation will not be voiced. Under the order of the procedure of granting academic degrees at St. Petersburg State University, approved by local normative acts, the session of the dissertation board is valid, providing 2/3 of the appointed board members are present, and the total number is not to be fewer than 4 people. Our dissertation board consists of 5 people. Everyone is with us today, including 3 members of the board who are working remotely. We have a multimedia connection with all the members of the board, as well as with our candidate for the degree. Therefore, we have a quorum. Our session should not last more than 2 hours, and the agenda is as follows. First comes the chairman's presentation about the documents submitted by the candidate for the degree and their conformity with the requirements. Then chairman's replies to questions, if any. Then candidate's presentation providing an overview and findings of the research. 15 minutes or a bit longer. Then questions on the candidate to the candidate regarding the presentation, no more than 2 minutes per question. Then candidate's replies to the questions, 5 minutes for all. Then reports on the thesis. The board members will be taking the floor in turns to provide their reviews and questions to the candidate for the degree, or maybe any offers. 10 minutes per speaker, per board member. Then comes chairman's report on the thesis, 10 minutes for that as well. Then candidates' comments about the reports on the thesis and replies to questions, 20 minutes for all. Then open discussion. Anyone present at the defense may state their position or ask specific questions on the thesis. 2 minutes per question. And anyone willing to speak out, please register in the registry form and introduce yourself before I give you the floor. Then chairman will ask the questions submitted during the broadcast via our website. Then the candidate's replies to the questions. Then presentation of the candidate's thesis supervisor. 3 minutes for that. Then a 5-minute discussion before the open balloting on conferring or non-conferring the academic degree. The discussion of the results of the defense is not broadcast. 5 minutes for that. Then open balloting, vote counting, and recording of the results in the protocol. Then we're going to make a decision on whether to confer the academic degree or not. And finally, we'll listen to the candidate's closing speech, no more than 2 minutes for that. Distinguished colleagues, any questions or comments or objections on our agenda? If there are no objections, let us proceed. But before we do that, I kindly ask you to switch off the sound on your mobile phones. Thank you. So let me start. The thesis by Valeriia Mulloiarova for the academic degree of the candidate of sciences in chemistry, specialization 02004, physical chemistry, is titled Hydrogen bond and proton transfer in self-associates and mixed complexes of phosphorus-containing acids. The thesis was approved for the defense by the order of the academic secretary of St. Petersburg State University, issued December 2nd, 2020, number 10930/1. Ms. Mulloiarova has prepared her dissertation at St. Petersburg State University, and Piotr Tolstoy, candidate of sciences in physics and mathematics, professor of physical chemistry department of St. Petersburg State University, is the thesis supervisor. 3 published works describe the major research findings. There are no papers published in peer-reviewed journals recommended by the Ministry of Education and Science, and 3 papers published in journals indexed in Web of Science and Scopus. The candidate has submitted the full set of documents to the academic secretary, and the above-mentioned documents comply with item 12 of section 3 of the order. And all the documents, as far as I'm informed, meet the requirements and are found in the certification file of the candidate for the degree, and the curator of the defense member of the Department of Dissertation Board Support has all the copies of these documents. And before I give the floor to the candidate for the degree, distinguished colleagues, I would like to ask you if there are any general questions to the candidate for the degree, and is there a need to consider the whole list of documents submitted by the candidate? No need for that. Okay, no questions. Okay, then, Valeriia, please, you have the floor. Thank you very much. My work is dedicated to the study of hydrogen bond and proton transfer in self-associates and mixed complexes of phosphor-containing acids in solution. Many organic compounds that have proton donor and proton acceptor groups are able to form hydrogen bonds. Phosphor-containing acids, due to the presence of PO and POH groups, are able to form several hydrogen bonds at once. Therefore, they are actively used as catalysts in organic catalysis, and they can be used in order to design the prospective proton-conducting membranes based on phosphor-containing acids. The mechanisms of complicated catalyst reactions and the reactions with proton transfer are poorly studied. We know that thanks to the presence of proton donor and proton acceptor groups, phosphor-containing and phosphinic acids are capable to self-association. And the previous studies using infrared spectroscopy has shown that in the gas phase there is an equilibrium between monomers and hydrogen bonded complexes. And at that, the equilibrium has shifted to the complex formation stage. And judging by the line forms, we've made an assumption on stoichiometry of the complexes, the formation of cyclic dimers with strong ties, and in certain cases they may reach 30 kilocalories per mole. And in crystals, such acids, depending on the substitutes, can form infinite chains or cyclic dimers. And self-association of such acids in solution is rather poorly studied. Therefore, the goal of this work was to develop the methods to define stoichiometry and the study of the structure and mutual influence of hydrogen bonds in self-associates and mixed complexes of phosphorus-containing acids in solution, and also in the establishment of correlation of spectrum NMR parameters with geometry and strength of the hydrogen bonds. And we've chosen phosphinic and phosphoric acids with different substitutes as object of the study. Self-association of acids in solution was studied using NMR spectroscopy. However, in room temperature, the lifespan of these complexes is rather insignificant. Therefore, the spectral parameters are averaged out along the set of complexes in the solution. Therefore, in order to achieve the set goals, first of all, we needed to shift the equilibrium to complex formation stage. To that end, we've assembled an experimental installation for synthesis, purification, and adding of liquefied deuterated freonic gases, trifluoromethane and difluorochloromethane. This combination of components allows the solvent to stay liquid and non-viscous up until the temperature of 100 Kelvin. We used still autoclave that was connected to a vacuum system with turbomolecular pump, and at the pressure of 10 to the power of -9 bar, we passed this compound through the tube with alkaline, then condensed it on aluminum oxide, and then this mixture was submitted to to a special area where it was stored up until the samples were added. Then we used the thick wall tube with young valve, and it allows us to have the pressure of 10 to the power of -3 bar, and NMR measurements were held at 100 degrees Kelvin, and it made it possible to observe signals with high resolution for complexes with different stoichiometry separately. And in order to establish the correlation of spectral parameters of NMR with geometry and strength of hydrogen bond, we've used quantum chemical calculations. The structure of complexes was established using the partial HD substitution of the bridge proton. Deuterization leads to weak perturbation in the geometry of hydrogen bond, and its distance is growing in complex with several hydrogen bonds. The deuterization may change the geometry and spectral parameters of the neighboring bonds. Thus, in cyclic dimer of acetic acid, we see the increase of the neighboring bond, and it goes along with HD substitution. And in homo conjugated anion, two donors of proton compete for the bond with one acceptor. Therefore, deuteration leads to the reduction of the neighboring bond, and it gives us positive HD isotopic effects. In complexes with high number of hydrogen bonds, HD isotope effects also grow in number. Thus, using NMR spectroscopy, we established that dimethylphosphinic and diphenyl phosphorus acids in Freon at 100 Kelvin form two types of complexes. For each type of complexes, we observe one single signal of a bridge proton. We can believe that hydrogen bonds in complexes are chemically equivalent, and this is possible if they are cyclic. After partial deuteration, the number of signals in the spectra is growing from 2 to 5. In this case, the integral intensiveness of the signal depend on deuteration stage, and depending on the deuteration stage of 43%, it will establish that one signal in the spectrum is referring to mono substituted cyclic dimer and two others to mono and 2 times deuterized cyclic trimer. And based on just one signal of monosubstituted form, we can believe that there is a quick triple or reversible shift of proton and deuteron. Otherwise, we would see two signals for each of the bridge protons. The analysis of low temperature spectra for other acids has demonstrated that in all cases the equilibrium shifts to the formation of trimer, and for some acids, dimers in detected amount is not formed. And the analysis of HD isotopic effects have demonstrated that their values are in the interval from minus 0.15 to minus 0.035. And such hydrogen bonds in literature are considered average or strong. And negative marks demonstrate the cooperative bonding of hydrogen bonds in all complexes. In order to understand what leads us to trimerization of phosphorus-containing acids, we've carried out quantum chemical calculations. And from the optimized structure of the monomer, we see that OPOH angle is not flat, and for hyperphosphorus acid it makes up 40 degrees. And the analysis of the function of localization of electrons has demonstrated that single pairs of oxygen atom of the PO group are targeted perpendicularly, and this leads us to conformation variety of the cyclic complexes. Therefore, the dimer and trimer can exist in two conformer groups, in two conformer forms that are different with the geometry of the ring of hydrogen bonds. In phosphoric acids, due to the opportunity of rotation, conformation variety is observed for monomers as well. Thus, monomer of dimethyl phosphoric acid can exist in the form of 4 conformers and diphenyl phosphorus in 5 conformers. All 4 monomers can form dimers in any combinations, and we may have 10 of such combinations. Therefore, it's not surprising that the number of cyclical trimers is even more, and from 20 possible options, 18 correspond with the local to the local minimums. The situation is different for diphenyl phosphorus acid due to the size of substitutes. Not all the combinations of monomers give stable dimers, and we could define just 4 local minimums. And in order to save the machine time, the studying of the structure of the trimer for this acid was limited by 1 conformer. Overall, in the work we've considered 71 structures for monomers and cyclic complexes for the range of 5 phosphorus-containing acids. Non-flat, non-plane structure gives us opportunity for conformation mobility, so the movement in the ring of hydrogen bond without its opening. The energy barriers of such conformation shifts do not exceed 2.5 kilocal per mole. And in cyclic complexes, we may have also double and triple irreversible proton transfer. Energy barriers for such processes make up 5-6 kilocal per mole. For phosphoric acids, the transfer of the proton was considered with the complexes with lowest energy, and it turned out that due to the overcoming of this barrier, one conformer of cyclic dimer shifts to another one. the height of energy barriers demonstrate that both processes will be quick in the NMR time scale, and in spectra the signals will average out for all conformers for all types of complexes. And in order to understand whether we're going to see this shift that will reflect the energy of the hydrogen bond, we've created correlations of the chemical shift of phosphorus depending on the energy of hydrogen bond in each of the complex. And it turned out that for all acids, this dependency is similar, and it's most observed for phosphinic acids, for which the change of energy per 1 calorie changes the chemical shift of phosphorus by 4 million parts. For non-symmetric phenylphosphine acid, we see the strong scattering of data, which is connected with the opportunity of orientation of the phenyl substitute regarding the ring of hydrogen bond. And we also established the dependencies of the chemical shift of phosphorus depending on geometry parameters, and phosphorus is most sensitive to the change of angle characteristics. And for phosphinic and phosphoric acids, these dependencies differ. When we mix two different acids, the number of signals in the spectra is growing. 4 signals were previously associated with self-associates of the acids, cyclic dimers and trimers. And 5 remaining signals are given for heterocomplexes, and after partial deuteration of the simples, the number of signals in the spectra is growing even more. And the signals, by the way, overlap with each other, which makes the interpretation of the spectra even more complicated. However, using the expansion of the experimental spectrum to subspectra, we managed to allocate 36 signals, 16 of them refer to heterocomplexes, namely cyclic, heterodimer, and 2 different heterotrimers that are different in content. The analysis of low-temperature spectra for other combinations of acids has demonstrated that in all cases the equilibrium shifts to heterocomplex formation, and not all the hydrogen bonds here are chemically equivalent, which gives us positive HD isotope effects in this chemical shift. And when we have a combination of diphenyl phosphorus acid with phosphinic self-associates, we don't see self-associates in detected amount, but we still see signals that do not refer to the previous complexes, and these signals were given to cyclic heterotitramers. And as we see from the spectra, the number of signals for this complex corresponds to the number of non-equivalent bridge protons in different isotopologues. And when we have one signal of non-deuterized form of tetramer, it means that it is formed by 2 monomers of one acid and by 2 monomers of another acid, which are bound into the cycle. Overall, in the work we saw 2 of such complexes, and you see one of them on the slide. And in the work we studied self-association and heteroassociation for 28 complexes of phosphorus-containing acids. Thus, we managed to conclude that the chosen phosphorus-containing acids in a protic environment form non-planar cyclic dimers and trimers, and the hydrogen bonds are cooperatively tied there, whereas in the mixture of acids we see the formation of heterocomplexes in which some hydrogen bonds are anti-cooperative. And using the analysis of HD isotope effects, we managed to prove the presence of quick reversible double and triple proton transfer in dimers and trimers, and we also established linear correlation of the chemical shift of phosphorus with the strength of hydrogen bond, and we provided correlation equations for quick assessment of the geometry of hydrogen bond, judging by the chemical shift of phosphorus. That's it. Thank you very much. Thank you very much, Valeriia. Any questions to Valeriia? No. Okay. Valeriia, I have a question. In the report, you mentioned that you substantiated that you need very low temperatures. And what do you expect? What will happen if you will increase this temperature gradually? What is the effect of this temperature increase on the conformation, equilibrium, on cooperativeness, anti-cooperativeness. So could you please say a few words on the topic? Well, basically, the signals of dimers and trimers give us a very narrow temperature range, and we expect that the equilibrium will change if we change the temperature. However, understanding how it will change it's impossible, because at 120 Kelvin, the signals of dimer and trimer can't be separated, and they spectrally form one signal. And as for cooperative and anti-cooperative characteristics, when we rise a temperature, this influence will remain. Thank you. Any questions, if any? No. May I? Yes, please. That's slide number 8, please. When you mention quantum chemical calculations, do I get it right that you've calculated just monomer, dimer, and trimer? And as for 4 molecules, clusters, you did not consider them? Yes, in my work, I've considered just dimers and trimers and self-associates. And I beg your pardon for interrupting. And you don't have clusters with larger molecules? That depends on the spectra. Yes? Yes, that depends on the spectra, because we considered quantum mechanically those complexes that we observe experimentally. Thank you. Thank you. Any other questions? Yes, may I? Yes, please. Could you please explain how you prepared your samples? Because there's a question, why do you have partial deuteration there? How did you do that? Do you mean how did I carry out deuteration of the samples? Yes, yes. Deuteration was carried out using methanol deuterium, CH3OD. So you can achieve any level of deuteration, but in order for us to see all the possible isotopologues, we should use 50% deuteration. And in order to make sure that the signals are correct, we used several degrees of deuteration. In some cases, we've taken 50% or more, in some cases 50% and less. But my question was about the control of the level of deuteration, if you can control that. We did not control the level of deuteration. It is controlled by when we add more methanol. If we want to get less, we add less, depending. So you can calculate these dependencies. Yes, how much do you need to add? Yes, we can calculate, but we did not do that. Then how did you prepare the samples, and were they made randomly? Were you lucky to get this level of deuteration? Judging by the experience of the previous year, we know that adding 20-40 microliters of methanol gives us the level of deuteration of 45-60%. Okay, clear. That's clear. Thank you so much. Any other questions? Yes, may I? Yes, Alexander. My question is the continuation of the question of Alexei. You mentioned the rise of temperature till 120 degrees Kelvin. If you rise it even more, well, we don't see the signals of dimers and trimers. We see just one wide signal due to this quick exchange, yes. And in freons it's not possible. But at room temperature, if we use some low coordination solvent of phosphorus-containing acids, for example, in sulfur carbon, Did you try to make it this way? Will you fix the signals of protons there? Or everything will be in such an exchange that you won't manage to sort that out? Well, with the rise of temperature, the exchange will be quicker in any case. Therefore, we expect that we won't see this difference of signals between dimers and trimers. Okay, the general question. You were dealing with the study of literature data on hydrogen bonds. Could you please tell me that we can talk about the degree of the transfer of proton in proton acceptor and proton donor groups, what is the percentage of this transfer? In our complexes, well, in your complexes, or maybe in some literature complexes? No, I haven't seen such a case. And can we talk about the barrier of activation of the protoning reaction? Do they have the activation barrier? Yes, they do. And how much is it? Well, it's hard to say, and I did not consider literature. Thank you. Thank you very much. Other questions? Okay, no questions. So let's shift to the next article of our agenda. The speeches of the members of the board with their reviews and the assessment of the thesis. And I offer the candidate for the degree to answer the questions after each review, so that it would be easier for our candidate for the degree and for the listeners to track the answers. So let's start with Professor Valeriia. So, distinguished colleagues, let me say a few words. The work of Valeriia is dedicated to such a fundamental process as hydrogen bond. That's one of the most important interactions in chemistry and biology. Without hydrogen bonds, we won't have life on Earth. Therefore, the relevance of the work is not questioned. The novelty is in the study of the complexes of new phosphorus-containing acids, and they are the objects of study. And the major and she used NMR resonance and the data of quantum chemical calculations in order to assess the geometry of the achieved complexes of self-associates. And as a result, she characterized the whole set of complexes. And what I liked most is that she got heterocomplexes between different molecules, and the author managed to sort out such difficult spectrums of NMR and give signals for each of the complexes. And I would also like to mention that the author of the thesis is not only a theoretician, considering the spectra, but also she is an experimental scientist, because the Freon synthesis is not that simple. They are quite costly, and Valeriia managed to organize such a low temperature synthesis because Freons are gases, even for an experienced chemist, that's not a simple task, and she managed to cope with that quite successfully. That's very good, and we have very good documentation for NMR spectra, and we can track all the references of the author into the different spectra, and we've seen it in the presentation as well, when all the data was documented by NMR spectra in good resolution. And now a few comments. Two major comments. The first one regarding the quantity of hydrogen bond, quantity strength of hydrogen bond. Can you use your NMR data to assess strength in kilocalories per mole? How can you do that? And second question, should I read out all the questions at once? Or should I read all of the questions? Okay. The second question, when describing the NMR method, I paid attention that this delay time for protons and phosphorus is rather high, 6 seconds. How did you select this time, and why did you select this delay? And a few questions on the filling out, documental filling out, because I have to read a lot of dissertations, and young scientists are very negligible regarding the source data, and Valeriia has given the sources quite randomly, because sometimes mostly they are ordered. And for example, the link 155, she gives the link to European Journal of Organic Chemistry, and the year was given as 1902. And by the way, this journal was founded in 1998. And as for 1901, this was the reference to Justus Liebig and Alan der Chemie. So you should have given the right link. And in our Russian tradition, some terms are more widespread, like proton donor or proton acceptor, and you give the copy from English. So that's not a principal comment, but still. these are not widespread terms. And overall, I would to say that the thesis by Valeriia Mulloiarova meets the requirements of the order as of September the 1st, 2016, on the procedure of granting academic degrees at St. Petersburg State University. And Ms. Mulloiarova, I believe, deserves the academic degree of the candidate of sciences in chemistry in specialization 000204 physical chemistry, and the article 11 of the above mentioned order is not violated. Thank you very much. Valeriia, could you please answer? I fully agree with the remarks, and I would like to specify that in my work I use the alphabetical order for references. That's one of the GOST recommended standards, and I understood already that I've chosen not the best option. And as for the question, can we conclude can we make a conclusion on the strength of hydrogen bond? As far as we know, all the correlations are not exact today because the relative values are easier replicated than absolute ones. And currently we have a lot of ways to interpret the chemical shifts of the bridge proton in order to assess the strength of hydrogen bonds. And in my work, I offer to use yet another parameter, the change of the chemical shift of the phosphorus. And as for the delay time, yes, this parameter was optimized, and it was taken just to be on the safe side. It's a bit more, and after 4 seconds we observe no changes in the spectrum. That's it. Thank you. Thank you so much. Alexander, are you satisfied? Yes, I'm satisfied with the answer. Dear colleagues, I forgot to mention that overall the reviews were already published on the St. Petersburg State University website, therefore there's no need to read them all if someone planned to. Okay. Now I want to give the floor to Denis Markelov. Please, Professor, you have the floor. Dear colleagues, hello. I also believe that the thesis of Valeriia creates a very good impression. She did a lot of work, she did a lot of experiments and theoretical studies. She used very good methods to achieve her goal. And she used quantum chemical calculations as well. I have a few remarks that certainly do not compromise the high appraisal of this work, but still there are some. Therefore, I'll just read them out, not reading the entire review. The first remark. That's rather a recommendation, not the remark. As for scientific novelty, you write that using quantum chemical calculations, you studied the dynamic processes in sulfur-associates of phosphinic acids. And here I don't agree completely with the wording that quantum chemistry can allow to study the dynamic processes, because the calculations are done in Kelvin when you see no speed or movement. And I would say that quantum chemical calculations here allow to interpret the dynamic processes that emerge in NMR spectra, in NMR experiments. That's what I would say. The second remark, that's page 549, formula 11 and 13. So something is wrong there with denominator. That's what it seems to me. If you have a look at image 20, when you give an illustration to the formula, it's obvious there that the sum of all curves in all points equals 1. And from these formulas, we can see that the sum is higher than 1. Maybe you've lost multiplying the denominator that should give us this result, so that the norm will be 1. Next remark. That's page 58, image 22A. Well, in the text everything is correctly, but One may be confused because due to this accumulation number for samples during deuteration, it's not sufficient. It's not sufficient to differentiate the signal from dimers. No, not from dimers. Sorry, from. So I'll open up the image to see. So the signal from dimers is like not differentiated. Maybe it's connected to the fact that in this spectrum you don't have enough of accumulation, so you just have it, but you don't see it. But not that they are fading away when you add a dimer. Once again, I'll repeat that in the text you don't mention that. You just mention the effect. Well, in the text everything is okay. Page 62, the end of paragraph 2. You're right that rearrangement in the complex with the opening or closure of hydrogen bonds is less probable at 100 degrees Kelvin, because they require the overcoming of significant energy barrier, and they would give significant temperature effects in NMR spectrum. It would be wonderful to hear to get the qualitative assessment of the characteristic time needed to overcome the barrier, and to compare this with the NMR time scale. So these are the basic comments. There are a few comments on misprints, but I believe that those are not important. The text is very well written, basically, and I don't have a lot of comments on the text for such a volume of it. So they are really negligible. I won't read them out. Because you just need to agree with them, and that's it. So the official phrase that I need to pronounce: the above-mentioned remarks do not compromise the credibility and the validity of the results and experiments. And the thesis by Valeriia Mulloiarova, titled Hydrogen Bond and Proton Transfer in Self-Associates and Mixed Complexes of Phosphorus-Containing Acids, meets the requirements of the order on the procedure of granting academic degrees at St. Petersburg State University. And Ms. Mulloiarova deserves the academic degree of the Candidate of Sciences in Chemistry in Specialisation 020004. Physical Chemistry, and Article 11 of the above-mentioned order is not violated. So certainly Ms. Mulloiarova deserves the academic degree. And that's what I wanted to say. Thank you. Thank you, Denis. Valeriia, please. Thank you very much for the review and for the questions. I agree with all the remarks, but I would like to explain about the phosphorus spectrum of dimethyl phosphoric acids. The spectra of the sample that has 7% of acid was registered with a lower amount of accumulation. Two other spectra registered at equal conditions. But during deuteration, the signal of dimer is expanding, and for just to add up the visual component, we expanded the spectrum of the sample for 55% of acid. And certainly I should have informed about that in the text of the thesis. As for the energy, the speed of proton transfer, I can say that the value of this barrier made up 5 kilocalories per mole. And roughly, using Arrhenius' equation, the speed of such a process won't exceed 10 kilohertz. And the spectral parameters are different by 300 hertz, no more than that. And at such speed, we expect full convalescence of spectral parameters. Thank you. Denis, are you satisfied with the answers? Yes? Yes, I am. Thank you. I'm satisfied with the answers. Okay, thank you. Now, I give the floor to Natalia. Professor Belkova, please. Dear colleagues, good afternoon once again. It's hard to give my report when I'm the third in line. Therefore, I'll just omit some of the details that were already mentioned, though I liked the work of Valeriia a lot, and I liked the text and the elegant results, the elegant presentation that she gave. And this elegancy hides immense work that she performed on not just measuring the spectra, but also the analysis of the spectra, and certainly decoding so many signals that she gets when she uses partial substitution and sorting out so many possible conformers, isomers, not just in experiments but in quantum chemical calculations. That's really that really requires a lot of labor, so I want to mention that. Certainly the dissertation is very well written. Certainly there are certain misprints that colleagues had already referred to, but overall the general impression is quite positive and quite pleasant. So, and certainly the candidate for the degree deserves the degree. And let's shift to the comments. One of them on the literature review, when describing the symmetry of hydrogen bond XHX on page 17, you write that such bond is considered as hydrogen atom that forms two bonds with an order of p1/2, and it is a 3-center 4-electron bond. And I would like to mention that the consideration of hydrogen bond as 3-center 4-electron is true for any hydrogen bond interaction of such type, so it's not necessarily that the proton should be just in the middle of the atoms. And yet another comment is regarding the literature review, where in the discussion of the correlation of the chemical shift N15 with the length of hydrogen bond, it's unclear why in porphyrins the value of the shift is monotonously growing and it becomes less negative when the distance decreases. And in the neighboring image, in collidine complexes with carboxylic acids, the value is becoming more negative when the distance decreases. I believe there should be the same trend. On page 57, there is a phrase that integral intensiveness of the signals in spectrum of dimethylphosphine and dimethyl phosphorus acids, that's compounds 1 and 2, demonstrate that there is a shift to trimer formation. However, if we consider this data, then for dimethylphosphine acid, that's true, and the correlation of trimer to dimer makes up 7:1, whereas for the second compound, this dissertation gives us the correlation of 3:2, which corresponds to the correlation of trimer to dimer as 1:1. Therefore, we can't say that there is a shift of equilibrium. And it's unclear whether there is a change of correlation trimer to dimer, depending on the concentration of the sample and temperature. The similar question arises to heteroassociates, when two different acids form such complexes. And this data would give us additional information on the stability of the studied complexes. And it's unclear what correlations did you use to say that the difference of enthalpies of hydrogen bonds, roughly 0.51 kilocalories per mole per bond, and what are the ties that explain this difference in different acids? So you mentioned that, but don't explain that. And terminological comment, when we talk about the copies from English, when you say hydrogen bond, hydrogen bounded. So you use less widespread terms in Russian for hydrogen bonded, and I didn't give it in my review, but that's a discussion linguistic question, how to call these interactions non-valent and non-covalent. So that's not a comment to dissertation, certainly. That's a Russian terminology issue that requires additional discussion among the colleagues, no more than that. And in conclusion, I'd like to say that the thesis of Valeriia Mulloiarova, entitled Hydrogen Bond and Proton Transfer in Self-Associates and Mixed Complexes of Phosphorus-Containing Acids, meets the requirements of the orders of September the 1st, 2016 on the procedure of granting academic degrees at St. Petersburg State University. And Ms. Mulloiarova deserves the academic degree of the Candidate of Sciences in Chemistry, in Specialization Physical Chemistry, and Article 11 of the above-mentioned order is not violated. So that's it. Thank you very much. Thank you. Thank you, Professor Belkova. Thank you very much for the review and for the questions. I would like to specify that Natalia mentioned it correctly, that any hydrogen bond is 3 cent for electron, and in this case I just missed the word covalent. That's what's the problem with this phrase. And as for the dependency graphs of the chemical shift of nitrogen between the proton and acceptor, I can say that in this case the image was taken from an article, and there was a misprint in the article, and for some reason there are some negative values there, and the spectra is published there as well, and we see that all shifts were positive. Therefore, the decrease of the distance from nitrogen to deuteron leads to screening of the nitrogen atom. And as for the concentration and temperature dependency in a dimer-trimer equilibrium, I've already mentioned that, unfortunately, the chemical shifts of dimer and trimer are allowed only in very narrow temperature range, and it's hard to assess where this shift will go if we change the temperature. And as for the concentration dependency, in our case the concentration varied from 0.5 to 500 and 1/10. And in such concentrations we did not see any changes. And as for the assessment of the energy of hydrogen bond, in this case the assessment was done based on literature sources, according to which the change of chemical shift of the bridge proton by 1 kilocalorie per mole, 1 millionth, leads us to the change of energy of 1.5 kilocalorie per mole. And for our acid, the difference of chemical shifts of bridge protons in dimer and trimers made up 0.7 million parts, and that corresponds to 1 kilocalorie per mole. And as for the question why for phosphoric acid this transfer of proton was considered for dimer with the lowest energy, I can say that the main goal was to demonstrate that the energy barriers are low and it does not exceed 5 kilocalories per mole. And as for dimers for phosphoric acids, we do not expect to get any new information. We were concentrated on phosphinic acids, and for phosphoric acids the image will be just similar, and there will be one exclusion that as a result of this shift we'll see the change in the conformation of the complexes. That's basically it. Thank you. Natalia, are you satisfied? Yes, I'm satisfied with the answers. Thank you. Thank you. So I have a technical failure. No, we see our professor already. Now I give the floor to Professor Polachak.
Yes, thank you. Do you hear me? Yeah? Everything okay? So first of all, let me thank the Commission for giving me opportunity to act here as a referee in this PhD degree procedure. At the moment, I don't hear what you say in the room, because I don't know why. But all the time I heard everything very well, and also the whole thing was very nicely translated on live, so I could follow presentation as well. So most of my comments were more technical, let's say, or editorial, so maybe they don't need to any particular comment from the side of the candidate, but I would like to refer to one of my comments, which perhaps would be nice to discuss at the moment with the candidate. So in section 4.4.2, author discusses cooperativity and anti-cooperativity of H bonds in phosphinic and phosphoric acid patterns. We could hear about it during the presentation. So, of course, the discussion is convincing for me. However, I feel the lack of the explicit estimation of cooperative and anti-cooperative effect, which can be expressed by the interaction.
Professor, just a moment, a technical break. I beg your pardon for that.
There are some technical problems.
Yes, there is a technical problem, unfortunately, Professor.
Okay.
We need...
Извините, пожалуйста, там у нас технические проблемы.
Yes, unfortunately, we have a technical failure, therefore we need to announce the technical break, Professor. Just a few minutes.
Okay, but I heard everything very well till now, yeah? But
Yes, Professor, just 1 second.
mainly technical or editorial, so maybe I will focus on the one which perhaps is worth to be discussed with a candidate at the moment. So in section 4.4.2, candidate discusses cooperativity and anti-cooperativity of H bonds in proper molecular systems.
Прошу прощения, дорогие присутствующие. Не был опять у нас технические проблемы.
Dear colleagues, I once again announce the technical break, unfortunately. Professor, unfortunately, we did not put the speech into broadcast, unfortunately, so I ask you to start once again. I beg your pardon for that, unfortunately. Yes, there was a technical overlap. We beg your pardon for that. Yes, from the very beginning, Professor, once again.
From the very beginning?
Yes,
okay.
Yes, thank you.
So now you hear me?
Да.
Yes, we do, thank you. Thank you.
Okay. So once again, let me thank the Commission for inviting me to act as a referee in this PhD degree procedure. It's very interesting new experience for me. Also, it's nice for me because the topic of this dissertation and the presentation of today is for me interesting and very actual. So most of my remarks in my report are more technical or editorial, so maybe I will skip them because I don't think they really need to be commented at the moment by the candidate. But I would like to mention one comment which perhaps is worth to be discussed today. So actually, in one of last sections of dissertation, candidate discusses cooperativity and anti-cooperativity of H bonds in proper molecular systems. The discussion is convincing for me. However, I feel the lack of the explicit estimation of cooperative and anti-cooperative effect, which can be expressed by the interaction energy and its components, including additive and non-additive contribution to interaction energy. Well, although experimental results indeed seem to very well support discussion in that issue, a part of my report, I will even say that I'm surprised that such subtle effects can be observed by experiment done by candidate. However, the interaction energy analysis would nicely strengthen the final conclusion. The more that it looks that author of the dissertation is familiar with computational approach, and the estimation of such energy components is not so difficult, let's say. But in general, my general expression is very good. I would say that both experimental and computational results in general fully support discussion and final conclusions. The presentation of the material is very clear and consistent. I would say the same about the presentation today. I could follow it because I had a copy of the presentation on my screen, and also everything was very nicely translated on live. So also the editorial part of the work is on highest level, and which is, in my opinion, very important in the context of PhD degree procedure. The main results of the work are presented in 3 publications published in high-quality peer-reviewed international journals. A part of my report, let me mention that in my country, it's explicit requirement for the PhD candidate to have such papers. So, in summary, I conclude that the thesis by Ms. Valeriia presents the results of an independent scientific investigation, and that Ms. Valeriia Mulloiarova meets all the criteria required to obtain PhD degree. Thank you.
Спасибо большое.
Thank you very much, Professor. Thank you very much. Valeriia, please, you have the floor to answer. Thank you so much, Professor, for the review and for the kind words. I can say that the analysis of anti-cooperative characteristics in heterocomplexes would be very useful for us, but unfortunately the methodological, it's not very clear how to organize it for non-symmetric heterocomplexes. We tried to model deuteration using artificial expansion of one of the ties in cyclic heterotrimer. And in one of the cases, indeed, two other bonds, protonated bonds, became shorter, but the change is so insignificant that it's hard to call it credible. Therefore, certainly it would be very interesting for us if you would tell us how to do that later on after the defense. I'll be very grateful. Thank you.
Valeriia.
Professor, are you satisfied with the answers? With the answer?
Yes, I'm satisfied. Well, you can really consider this remark as advice for the future, because of course always there are some methods or things which can be still do. So this is the science. Yeah. So of course I'm satisfied fully.
Спасибо большое.
Thank you very much. And my review is the last one. I'll be short as well. What I want to say is that this thesis has all the components of the classical good dissertation required by the Higher Attestation Commission of Russia. The relevance of the topic is quite obvious, as well as the scientific novelty and many new results that were achieved, many developed methods, and theoretical correlations offered, as well as the practical value is not questioned, and the validity of the results, and also the substantiation of conclusions. Though there was certain criticism on the technical component of the dissertation, I believe that I would mention the exact logical structure and a very good, concise Russian language. Certainly that's an advantage of this thesis. That's what I wanted to mention. Still, I had 2 points that I wanted to mention. One is a general remark. The proposed experimental method of the definition of molecular complexes in liquids is worked using low temperature solutions of phosphinic and phosphoric acids and freons. At the same time, you substantiate the choice of these systems. However, it would be wonderful to discuss what physical chemical problems that would be resolved by this discovery of low temperature behavior in the work of these solutions. What are the principal limitations of the developed experimental method, and what are the application limits of these correlations? And that is true for proton conducting membranes mentioned on page 121. Unfortunately, the text of the thesis gives us no answers to this question. Second remark is a private one, dealing with a graph. And Valeriia, I believe you can show this picture. That's image 44, and the data was correlated using linear correlations. Compared with the text of dissertation, you don't have this cloud of points in the middle. And the question is, can we talk about linear correlations discussing the data given here on image 44? Because the only set of points evenly scattered across the x-axis is not described by line, it's rather a cloud, and other sets of data have certain scattering character as well. For example, they are on the margins of the intervals, and certainly we can draw a line through each of these couples. Do you have any independent basis to use this linear correlation here? But certainly this remark does not compromise the high appraisal of this work, and the thesis by Valeriia Mulloiarova, titled Hydrogen Bond and Proton Transfer in Self-Associates and Mixed Complexes of Phosphorus-Containing Acids, meets all the requirements of the order on the procedure of the granting academic degrees at St. Petersburg State University. And I am sure that our candidate for the degree, Ms. Mulloiarova, deserves the academic degree of the candidate of sciences in chemistry and specialization physical chemistry. And Article 11 of the above-mentioned order is not violated. Thank you. Thank you so much for the reviews, for the review and for the questions. They were quite hard to answer. And as for specific chemical and physical goals, problems that can be resolved if we apply this method, proton conductivity depends on the length of hydrogen bridge. And in our work, we provide a correlation that allows us to define, by the change of chemical shift of phosphorus, we can define this change in the bridge length. Therefore, the correlations can be used to study the influence of some external factors on the proton conductivity in some other polymer chain. And as for the limitations, certainly the main limitation here is the need to fully shift the equilibrium to complex formation. And we need high concentration of POOH groups in the polymer. And we believe that the fairness of this correlation is limited to our complexes, but maybe the correlation will be also applied for other systems in which POOH groups will be involved in the formation of at least two hydrogen bonds close in energy. And as for the linear correlation, you mentioned it right, that in fact this line is drawn through 2 points, and we see the scattering of data points. But this scattering of data points is connected with the influence of substitutes. Therefore, we believe that if we can minimize this influence, then this entire cloud of points will be reduced to 2 points, one for dimer and another one for trimer. And if we draw a line through them, then the tilt of 4 millionth will remain, and we can check it using experimental data. And in this case, you see the graph of dependency of experimental values of the chemical shift of phosphorine, dimer, and trimer for 3 acids that form these dimer and trimer complexes. And depending on the chemical shift, this energy of hydrogen bond received experimentally can be calculated from the chemical shifts of the bridge protons in dimer and in trimer. And as we see from the graph, the tilt, the angle received by experimentally and from quantum chemical calculations for dimethyl phosphor acid corresponds with high accuracy, but that's not true for the second sample. And for phosphoric acids, this tilt makes up minus 2.7 million parts for 1 kilocalorie per mole, and in case of experimental results, minus 2.6 million parts. Therefore, we believe that this dependency is well grounded. Thank you very much. It's clear for the second question. And as for the first question, do I get it right that indeed there's a transfer to other systems, and the principal limitation here is the cryogenic temperature? So all the physical, chemical problems to be resolved, they are limited by cryogenic temperatures. Do I get it right? Yes, it was achieved in low temperatures in our experiments. Okay, I'm satisfied with the answer. Thank you. And yet another question to the members of the board. Is everyone satisfied with the answers? Maybe some. Okay, as I see, everyone is satisfied. And now we give the floor to the people who are not members of the board. If anyone is willing to speak out on the thesis. No, no one? Okay. Now, the questions that were submitted during the broadcasting online on the text of the thesis and on the presentation. Did we get such a feedback? No, no such questions submitted online. Okay. Now, I give the floor to the thesis supervisor. Piotr, please, you have the floor. Tell us a few words about the candidate for the degree. Yes, dear colleagues, hello. I have a very good impression of this work. Some of the results required, such a level of skill that not everyone is able to show. And Lara became the main expert in low-temperature NMR experiments in our lab. The synthesis of the synthesis issues, they are all now controlled by Valeriia. And quite recently, we also have students, 2 master students, Sasha and Adam, who are working under the guidance of Valeriia, who are performing the experiments. Thus, I believe that Lara is really one of the members of our group. She participates in a range of projects that are performed by our team. And the fact that she is able to simultaneously work on several projects at a time is supported by the fact that her publications are, there are much more of her publications than the ones given for the defense. And in this work, Lara is demonstrated such qualities as industriousness. She is very responsive. She has all the necessary qualities. And in spring this year, she will participate in the contest for one of the positions in our lab. So I believe that we will continue to work with her in the Institute of Chemistry of our university, and I'll be very happy to see her there. Thank you very much, Piotr. Distinguished colleagues, distinguished guests, as we are holding our session online with members of the board who are working remotely, I wanted to ask if any of the members of the board have any questions. Maybe the candidate for the degree has any questions that we did not cover. Maybe some comments connected with this work in the remote mode. If there are any such questions, I kindly ask you to ask them. Okay, no one. Anyone present at the board session? Does anyone want to speak out? Any other questions submitted online? No. Okay. Okay. Then we stop taking questions. And it's 3:15 p.m. and we shift to the vote. And before I announce the roll call vote, I ask the members of the board. Now we have an opportunity to, before the start of the vote, to hold a short session to discuss the results of the defense. And this will not be broadcast. How do you think? Do we need such a close discussion, or are the results clear already? I don't think so. No, we don't need this close discussion. Okay, thank you. Okay, if there is no need for that, we continue our session and we shift to the roll call vote. And I solicit the opinion of every member of the board. You should declare your opinion privately or publicly. And let us start. Alexander, what's your opinion? Yes, I vote for the award of the academic degree to Valeriia in physical chemistry. Okay, thank you. Alexander. Professor Markelov? Certainly I vote for as well. Professor Belkova? I vote for the award of the academic degree as well. Professor Polachak?
I vote for giving the academic degree to the candidate.
Thank you very much, everyone. And my opinion is just the same. I certainly vote for the award of the academic degree to Ms. Mulloiarova. So, that's basically it, distinguished colleagues. I would like to announce that out of the 5 members of the board who participated in the roll call vote, 5 members voted for the award of the academic degree, no one voted against, and no one abstained from the vote. Thus, we award the academic degree of Candidate of Sciences in Chemistry to Ms. Mulloiarova in Specialization 020004, Physical Chemistry. Distinguished colleagues, due to the fact that we hold our session online, I would like to ask the members of the board or the candidate or anyone present has any comments on the procedure of our session. So I solicit your answers. No, no, no. Denis? No. Professor Polchak?
Everything clear.
Well, then I give the floor for the finalizing remarks to our candidate for the degree. I would like to thank the members of the board for their reviews, for being present, for their work, and I would like to thank the organizers of this defense, and I would like to thank my Thesis Supervisor, Professor Tolstoy, and the whole team of our laboratory for being there for me, for creating such a favorable environment for work, and I'm very grateful to them for their support and for their help during the entire process of this preparation of the thesis. And I would like to thank Vadim Kukushkin, who admitted me to St. Petersburg State University. He was my conductor in this university. And I would like to thank everyone for coming, my friends, my family, and those who are watching the broadcast online and who was unable to be here because of pandemic. Thank you for not letting me stop and help me to move forward when I was feeling down. Thank you very much. Let's congratulate our candidate for the degree. And we close our session. Thank you very much. And I kindly ask to turn off the broadcasting of the conference.